Let's talk about angular impulse and momentum. So, if you want to find the rotational form, it's going to be the integral of tau, the derivative of t, which is equal to the change in the angular momentum. And that's basically integrating it. That's the calculus approach. But for AP Physics 1, you just find the area underneath the curve of torque versus time, and that area is just going to be angular impulse. And in order to find the translational form is F times delta t, which is equal to delta p, which is the change in the momentum. So, and you also know that's from P equals mv. And the rotational form of that is just L is equal to inertia times the angular velocity. So, again, you can see down here that the area under the curve is going to be equal to the angular impulse. And also remember that if you have torque that is constant, then you just multiply torque times time. Now let's do an example problem. So let's say we have a boulder of 20 kilograms and radius of 0.20 meters rolls without slipping down a hill 15 meters high from rest. The rotational inertia for the boulder is I is equal to 2/5 mr squared. Now first we're asked, what is the angular momentum? What is halfway down the hill? So how do you start out with this? Well, what we can see is let's first draw this out as a triangle. So drawing this out, we can draw the ball in two positions. And drawing it in two positions, we have 15 meters here, and then we have a circle right here, and that's going to be 20 kilograms, and then this is going to be 0.2 meters, and then we have here the ball is slightly lower, v is equal to 0, and the ball has been rolling. What is the angular momentum down the hill? So you want to know the omega at this point. So we use conservation of energy. So by using conservation of energy, well, we just have the system. We're going to define the system is equal to Earth plus the boulder. So that means the W is going to equal to 0 because the frictional force doesn't do any work. The work of FF is equal to 0. Let's write that more like W. And also we know that it doesn't do any work because the normal force and the gravity aren't going to do any work. Fn is equal to 0 and Fg is going to equal to 0, right? So we know that the initial energy, how can we find the initial energy? Well, we know that it's halfway down the hill, right? Let's make this a bit more clear. That's halfway down the hill. So this is going to be like here, and then this is going to be like up here, right? So we just have that is equal to mgh. Mgh is just the potential energy, which is just equal to 7.5. We know the mass is just equal to 7.5, and then we multiply that by mgh, or just mg. The height is 7.5. Now, we know that EF is going to be equal to 1/2 mv squared plus 1/2 of I inertia times the angular velocity. And actually let's make a little bit more room for this by moving this down. Let's make this a little bit easier. So now our next step is that we know that V is equal to the radius times omega. So now we know that that's omega, right? Like, what we can do is, let's just make this into blue, right? Make this into blue too. Well, we want to sub in there. So we're just going to have 1/2 is equal to m times r times w, and then we're going to square that, plus 1/2 I 2/5 w squared, because that is the formula for the inertia that we have to know. We can write that actually as 2/5 squared. So now you have m squared plus, that will cancel. So now what we can do is we have w squared is equal to 1/2 times mr squared plus 1/5 mr squared. And this is because we can see that the 2 and the 2 here, that cancels out. And then over here with the w squared, we see that we can just factor out, because we see the w squared here, we see the w squared here, and we see the w squared here, so we can just factor that out. So we just have that expression, and now we just can move this down here. We have w squared is equal to 7/10 mr squared, and then this is going to equal to 7.5 is mg, right? So we can cancel out the m. So therefore, we're left with omega is just going to equal to the square root of 7.5 times 10/7 divided by r squared. And then, okay, let's make this a little bit more clear that that's down here. And then plugging this into our calculator, we get 51.8 rad per second as our solution for the angular velocity. And now but we want the angular momentum, right? Angular momentum. And in order to get the angular momentum, we use the relationship again. L is equal to the moment of inertia times the angular velocity, right? So that was just equal to 2/5 mr squared times w, because this is just going to be our I. This is going to be the moment of inertia for the shape that we have, and that's going to be division sign. So now plugging in our values, we have 2/5 times, let's actually make that orange. So we have 2/5 is 20 times 0.2 squared times 51.8. Actually, let's make that blue. Why not? This all blue. Now this is gonna, plugging this into our calculator, we have this is gonna equal to 16.6 kilograms meters squared over second. And yeah, so now we want to find the angular momentum at the bottom. Let's continue with this. So in order to find the angular momentum at the bottom, we have w is equal to, well, the initial, okay, so the only thing that's going to change for the angular velocity is you're going to go down 15 meters, right? So that means the initial energy is going to be, E initial is going to be equal to 15. But if you make h equals 0, and then everything else will be the same. So you're going to just do all of that. Now you're going to have 15g times 10/7 divided by r squared. And then what is this going to give you? Just type this into your calculator, and then you get 2.9, oh no you don't, you get 273.2 rad per second times I. Multiply that by I. So now we have 2/5, 20 times 0.2 squared. That's going to be 23.4 kilograms meters squared per second. Now what is causing the change in the angular momentum? Let's actually move this down. So we know that tau is equal to tau times delta t, right? And then this is going to be, this is the static friction force. But we're rolling down, but so that's only one thing. That's the only thing causing force. A torque. So that's the angular and that causes angular impulse. An angular impulse, and what angular impulse does, angular impulse is what changes, okay, that's required to change, to cause a change in angular momentum. So now let's continue now. Okay, so we have this. So let's put this all together. Let's do another problem. Now, okay. A system consists of two small disks. of masses m and 2m attached by a rod of a negligible mass of length 3l as shown. The rod is free to turn around a vertical axis around point P. The two discs rest on a rough initial counterclockwise angular velocity w0 about P. The system is gradually brought to rest by friction. Develop expression for the following quantities in terms of mu, m, l, g, and omega initial. The initial angular velocity of the system about the axis through P. So how can we start with this? Well, we know that for A, we know that L initial is equal to IW, and we know that 3L is going to be negligible. So we just have two objects basically. So it's going to be, we're just going to rewrite this as 2ml squared plus m times 2l squared, right, times w initial. And then if we, okay, move this away. Well, if we plug this in, we're going to know that that's L, that's 6ml, distributing that, W initial, distribute that. Now, okay, for B. The initial angular momentum of the system around about the axis through P, or the frictional force acting on the system about the axis through point P, through P. So we know that this is going to be 2mg. And then we know over here, this is going to be equal to mg. And why? Because it's double the mass. And then that's Fn, 2, that's Fn. And we can also label that F is like this. And also F is like, F is like this. And then this is going to be like center, right? So it's going to be opposing the motion as it's spinning around. It's going to be opposing the motion as it's spinning around parallel to the plane. But it's the only thing that's going to exert torque, which is the mg and the normal forces. They kind of cancel each other out. Right? So friction and torque and friction and force and kinetic friction. So the torque is that thing over there. So it's going to be like, you have that, right? You have L here, so you're going to have tau is equal to F of the mass that's 2m. You can have FFm times 2L. And then when you move this down here, you're going to have mu times 2mg. That's friction force, right? That's friction force, right? So plus mu mg times 2L. And that's going to equal to, multiply that out. Multiplying those, that's going to be -4 mu mgl. And we can imagine that the acceleration is going in this direction, right? That's going to be your answer. That's frictional torque. Now for C, we have tau delta T is equal to delta L. And we know that LF, what is this? The time at T at which the system will come to rest. So you have LF, that's going to equal to 0. So that means you're going to have -4 mu mg L T is equal to 0 minus 6 ml squared W initial. So that means you can cancel these out there. So then you just have, make that more clear, that that's tau. It's going to equal to 6L W initial for UG And that's going to equal to 3 over 2 as a simplified fraction form, LW over UG. And that's going to be your answer. All right, thanks for watching.